How was your weekend? They always are. Somebody was telling me in Germany they do half-day Fridays, they have longer book and they do like much more productive work days because of that. Bless you.
Thank you.
I think it's a good idea. I'm still chewing on the cookie. It was pretty good though. Do you know where they came from?
Grotto.
Probably the best before I ate it.
Too late now.
Found it on the floor. Found these cookies on the table. I got my car back. I was saying at the beginning. That's exciting news for me this weekend.
Pass around.
Thank you.
Go out. You got it.
Tired.
I'm in the middle.
But it's good to have it back. I feel mobile again. So, we're in week 2. I think by the end of this week, the first homework assignment is due. Anybody having any trouble accessing the homework? You're going to call it that? Did anybody start the homework assignment? Are you having any trouble getting through it? Is it okay? It's on. All right. I don't see it from your side, the student point of view, so I don't know what it looks like. So I only see it from the editing window. So as long as you're able to access it, it should be working fine. Yeah.
I'm just humble myself, to be honest. I can't even get to the first problem. I looked at the PowerPoints. Have we covered the iteration to solve the first? It's a unit conversion.
The unit conversions we've covered, but the Coulomb's law we just introduced. We're going to use Coulomb's law problems today,
Okay.
and the majority of the homework is Coulomb's law.
I think it's a unit conversion, or maybe it needs a unit conversion and then some
Well,
thing.
on that topic, if you are doing the homework and you get stuck on something, it's not a bad idea to come talk to me about it. Because there's twofold benefit to that. One, I'm pretty helpful on these kind of things. You've got come to my office before, and I think I'm generally pretty helpful. And two, it gives me information because this is brand new. This homework system is brand new for me. So I don't know what it looks like. I don't know what it looks like on your end. I don't know how it asks the questions to you because I can't see that from the teacher side. So it's a benefit to me because I get to see it, and it's a benefit to you because I will help you and we'll make sure you get the right answer. And if for some reason I can't find the right answer, then I know that's not a good problem, and I need to take that one off and put a different one on. So please do. I mean that sincerely, like not just words, but real actual meaning here. You do come and see me if you're stuck on a problem. Fair enough? All right. If after today you're still not able to do any, then we need to talk. All right? So the plan for today on that topic is to, one, quickly review some of the stuff we talked about last week, conductors, insulators, how charges move, and Coulomb's law, which we introduced last class. And then I want to do at least 2 problems solving Coulomb's law problems, where we have 2 different charges and we're going to find the forces between them. And then at the end, the plan is, if there's time, talk about the superposition principle and what happens if you have more than 2 charges. If I have one charge thing here and one charge thing there, Coulomb's law is great because there's Q1 and Q2. But what if there's more than 2? So there's here, here, and here. What if we have a whole bunch? And that's normally how it is. Normally you have a lot of different charged stuff in a localized area, and they're all interacting with each other. In order to solve that, Coulomb's law isn't enough. We need to use it iteratively. We need to use multiple iterations of Coulomb's law, and that's called the superposition principle, which leads into our next lesson next time about electric fields. All right? So that's the plan. That's how I laid it out in my brain. We'll see how it goes. All right. It says it's on, but it doesn't appear to be on. Oh, it's on. I was listening to the Art of War on the way to school, so don't mess with me. All right, what do you recall from last week's lessons? We talked about a whole bunch of different stuff. Don't say nothing, that would depress me. What did we talk about? We talked about charges. There's 2 different kinds. What are they? And where do those come from? Protons and electrons. Yep. Every single electron has a certain amount of charge. Every single proton has a certain amount of charge. As it turns out, they have the same amount of charge, which is nice because that allows us to exist. in the universe as we are. If it wasn't that way, things wouldn't be the way it is here. Like everything would be different. I don't know exactly how it would be different, but it certainly would be. How much charge does each one of those things have? Yep, 1.6 times 10 to the minus 19. A tiny little bit, little itty bitty amount, but that's because there's a whole bunch of them, right? You have many, many electrons and many, many protons inside of you, and each one of them has that certain amount of charge. So when you build up a substantial amount of electrons, or a substantial amount of electrons are given away from you, then you do get a non-trivial amount of charge. All right, cool. So we said they move around, the charges move around. They aren't created or destroyed, but you can take charges from one place and put them somewhere else, right? Conservation of charge. They don't just come from nowhere, they come from neutral atoms, but we move charges. What's the thing that does the moving? Usually. What's that? Usually it's the electrons that do the moving. Normally the electrons go from one thing to another. So if I give up a bunch of my electrons, I become more positive because I've given up negative charges. If I take some of your electrons, I become more negative. Even though I'm gaining something, I'm becoming more negative because I'm gaining negative charges. Even though it is the electrons that do the moving, when we start drawing circuits in a few weeks, when we draw the movement of charge, that's called current, and we draw the arrow for current, the vector for current, in the direction of what positive charges would be doing. It's the convention that was established before we really knew what was going on. But the good news is it really doesn't matter. It's just important to know what's actually happening so that we can conceptualize this stuff happening in the circuit. You can't really see electrons moving. You can see the effects of it. They're just too small and too fast. So because we can't literally see them moving around, we have to visualize it and conceptualize it. So it's important that you know what's really going on. Even though mathematically we draw it in terms of positives moving, it's really the negatives that are actually moving. Fair enough? All right, cool. Some materials hold on to their electrons real tight. You know what we call those? Say what? You're thinking about stuff that like tries to get electrons, but I'm talking about stuff that just doesn't let their electrons move. The electrons are held onto the atoms really tightly. Insulators or dielectrics. So those are synonymous terms. An insulator, a dielectric, we use the terms interchangeably. Those things don't let electrons move around very much. So if I hook up a battery to it, a voltage source, that wants to make electrons move, the electrons are still not going to move very much. When I was a kid, my grandparents had horses, and they had an electric horse fence. And as with all kids, I made sure I touched the fence at least once in my life because you have to see what happens. And it's a wild sensation. You touch it, and like I felt a pop on this side and a pop on my foot, and like a jolt through me. That was me feeling the current going into me and coming out of me on the ground. It's trying to get to the ground. I only did it once because you only need to find that out one time. But I quickly learned you don't want to do that. So instead, I would take a stick, a dry stick, I'd lift up the wire and go underneath if I wanted to go in the pasture or go in the woods or whatever, go outside and play. I was a conductor. My insulative properties weren't enough to stop the voltage from moving a current from me to the ground. But the stick was a good enough insulator that it didn't let the current go through. It has what we call a high resistivity. That's something we're going to cover in a lot of depth when we get into circuits because resistors are a really important part of the circuit that we're going to cover, like I said, in quite a bit of depth. Bless you. But there's no such thing as a perfect insulator. If the voltage on that fence was high enough, even that dry stick would still conduct. We could still move electrons if we forced them hard enough. Voltage, also known as electric potential, is the push to make charges move. And if you push hard enough, the charges are going to move, even if it's an insulator. Similarly, there's no such thing as a perfect conductor. There's always some resistance, even inside of a good conductor, like a copper wire. Or gold is a really, really good conductor. That's why they use it in keyboards. And even that has some resistance in it. There's no perfect, except for superconductors, which we'll talk about again later in the semester. Superconductors, under very specific circumstances, get essentially zero resistance. But that's the only exception to the rule. All right, that's a lot of words. Any questions about that stuff so far? It's all reviewed. We talked about all this stuff for the most part. Now, more stuff that I learned as a child playing on the farm. If the stick wasn't dry, you'd still get zapped. How come? Now, water itself, if it's pure, if it's distilled water, is an insulator, believe it or not. But most water isn't pure and distilled. Most water that we encounter has minerals and things in it, which allows it to conduct. And it's a pretty decent conductor when it's not distilled water. Two things that have the same charge, they're going to feel a force between them. The electrostatic force, that's what Coulomb's law is all about. What direction will that force be? Say it out loud, own that stuff.
Propulsion.
It's going to repel. If you have two like charges, whether they're both positive or both negative, are going to repel from each other. If they're opposite charges, there you go. Yeah, ride that wave. You're on a roll. They're going to attract each other, absolutely. So a positive and a negative, whether this one's positive or this one's positive, if they're opposite charges, they're going to feel an attractive force. Let's say I have two hanging spheres on strings. They call them pith balls. I don't know what that means exactly, but it's a common physics demonstration. We have them somewhere in the lab, but I didn't have time to grab them. So it's just very low mass string, very low mass orb of some kind, like styrofoam or something like that. And you charge them up. If they have the same charge, they're going to hang separate from each other. If they have the same charge, they're going to hang right next to each other. So I'm going to give you a couple different scenarios, and we're going to decide whether, if I let these things go, they're going to come together, if they're going to end separated or end together. Does that make sense to you? Okay, so I have two spheres hanging like so. Let's say they're made out of a conductive material. So they've got like a foil coating around the outside. One starts with a net negative charge, a small net negative charge, and one starts with a small net positive charge, and I let them go. What's it going to do? They're going to attract, they're going to touch, they're conductors. What are the charges going to do? Well, one's positive, one's negative. The positive wants electrons. The negative has extra electrons. So those are both Q, so they have the same magnitude of charge. So what's going to happen? They're going to neutralize. You were thinking the right way. We just had to take the next step logically in your mind. So the electrons from the negative are going to move to the positive. It's going to be overall neutral. And gravity is still a thing, so what's going to happen? They're just going to hang there, right? There's no electrostatic force between them because they neutralize each other. They're conductors, so the charges are free to move, and boom, they end up together. That's nice. It's a nice story. They started apart, they end up together. It's pleasant. It's like a Hallmark movie, right? All right. I'm erasing that. Now I have this one over here. It's a positive charge, but it's a big positive charge. And this one over here is a positive charge and a small positive charge. They're still conductive. They're the same exact spheres. We've just changed the initial starting conditions by giving the one a really big positive charge, giving the other a fairly small positive charge. What's going to happen? They're going to repel. They might not even, if it's a strong enough charge, they might not ever come in contact with each other. I let them go, and there could be enough charge that they're held apart. The electrostatic force might be bigger than the gravitational force pulling them together, and they might not ever even touch. If they do touch, what would happen? They're still going to repel, right? Because there's a total net charge of positive. We're not going to get a negative charge just magically out of nowhere. The big one is going to pull electrons off of the little one until they reach an equilibrium. But they're still both going to be positive. The big one is going to be slightly less positive. The small one is going to be slightly more positive. They're going to reach an equilibrium, they're going to separate, they're going to be apart. That's sad. Maybe more realistic though. They came together briefly, but then they separated, never to be together again. Physics is dramatic. Yeah? Yeah. Okay. let's change the initial position of this one. Let's make this one negative. This is a tricky one. Let's make the big one have a large negative charge. And the other one, they're still conductive. And the other one has a small positive charge. Now, instead of me doing the talking, why don't you talk to somebody nearby? There's a room full of really smart people. I've been consistently impressed by your contributions to class, and I want to hear what more people have to say. So why don't you talk to somebody nearby who looks smart? Oh, that's mean. That's so mean. Oh my gosh, that's mean too. You're cooking. You guys are
I'm cooking.
oh, fair enough.
So what I don't know if we what would happen is they both be
They attract, but this will eventually become
All right, who out there talked to somebody who had something really smart to say?
I did.
Did you?
Yeah.
Awesome. If the person sitting next to you didn't raise their hand, which is most of the people in the room, I'd be a little bit upset. Like, I told you something on top before, you didn't even raise your hand? All right, well, what did your friend say?
What did you say?
It was smart. It's hard to pick it all up. I get it.
I think they're both going to be negative
Okay, why?
because the electrons from the big one are going to go over to the positive charge, but they're still going to be at net charge and negative. And then they kind of equalize there, but they still be negative.
That was really smart.
That was really smart.
I'll need to say it again. Well, it's pretty smart. It's just very quiet. Sometimes smart is subtle. You can still be smart and quiet, but in this room we want to be a little boisterous. We want to own our physics a little bit. There's no fear of making mistakes here, right? We just want to be heard more than anything else. So I'm going to translate. You tell me if I get it right. So that negative charge is a big negative charge. And that means that there's lots of extra electrons, which really don't want to be near each other. So it really wants to get rid of those extra electrons. It's got a big charge. By the way, a little caveat here. Next week we're going to talk, maybe even this week, I don't remember the schedule, but in the not too distant future, we're going to talk about something called electric potential, also known as voltage. That's the amount of push to push charges either through a circuit or from point A to point B. You're making a connection right now. You said that large negative charge has a lot of push to push the electrons off. So the amount of charge on an object has to do with how much potential it has. So keep that in the back of your mind when we get to electric potential. It has to do with the amount of charge on an object. Good call. So that positive wants electrons, but it's only got a little bit of a positive charge. So it's small relatively. So it only kind of wants electrons, but that big negative one really wants to push those electrons off. So when they come in contact, that large negative charge is going to give up lots of electrons. It's going to fill up the slots that are missing electrons for that small positive. But then it's got a neutral charge. It doesn't really want electrons, but that negative one had a large negative charge. It's got lots of excess. So it's going to keep giving it electrons until we reach some kind of equilibrium. Till the push one way is equal to the push the other way. So the voltage on one is equal to the voltage on the other. At that point, they have the same charge, but what charge is that going to be? It's going to be negative. Again, we can't just make positive charges out of nowhere, and we have a ton of extra electrons in this. So that large negative charge is going to push the excess electrons onto that now neutral sphere, giving them both a net negative charge. When they both have a negative charge, what are they going to do? They're going to repel. So they come together, they exchange information, and then they repel. I guess they didn't get along. They weren't compatible. It is, but you know,
That's life.
it is life. And I guess it's better than the alternative. What if these are insulative? What if they're insulators? Let's go back to the first scenario we had. The very first scenario, where we have a positive and a negative. They're equal in magnitude, but they're not conductors this time. they're insulators, which means they don't really easily give up their electrons. What do you think is going to happen now?
Nothing.
Nothing at all.
Nothing.
I let them go and they don't move.
Yeah.
I don't think that's true. But do you have a rationale for that? Do you have a thought process?
Well, if with an insulator, like the electrons stay within, is it within the nucleus, is it?
No, the electrons are around the nucleus, but they
Okay.
stay on the atom.
Okay, so
Generally.
my rationale is that they would just, like, that bond would be
Oh,
stronger.
okay, I understand what you're saying.
Yeah.
The nothing is, okay, I spoke too
Yeah.
soon. So the nothing is, you don't think the electrons are going to move around.
Yeah,
Well, what's going to happen to the spheres? So you're looking microscopic. You're like a step ahead.
yeah, exactly.
All right, you're thinking up here, and I'm just thinking down here.
Yeah,
Okay, that's really good thinking. So you don't think they're going to move around much, but let's zoom out and look at the spheres as a whole. One's positive, one's negative. What force are they going to be?
attraction.
And also gravity is going to also pull them down, right? So they have two different forces pulling them towards each other. Okay, so maybe the electrons aren't going to move very much. They're going to move a little bit, but probably not very much. That being said, they're still going to feel forces towards each other. There's no forces pushing them away from each other. So I just didn't understand you. I'm sorry, I didn't mean to make you
It's
do
okay.
My default reaction is snark, like a little snarky kind of.
No,
You know that. You've had me in class.
I do know that.
So, but it was preemptive snarkiness, and you didn't deserve that. So, what do you think is going to happen? And end of the day, what happens to the spheres?
Would be attracted.
What's that?
Would be attracted.
They're going to be attracted. So they finish in contact with each other. One of two results, right? They're either going to finish in contact with each other or finish apart. In this case, they're going to finish in contact with each other. Let's do a couple more real quick, and then we'll move on.
Do the charges stay like negative and
So-
positive still?
The parts that are in direct contact with each other, the charges will probably move, but it's not going to pull charges from other parts of the sphere, likely. It depends on a few different factors. It depends on how conductive and how insulative the material is, because remember, there's no perfect insulator. It depends on whether they rotate around and kind of like, if they're able to roll and touch multiple parts of the sphere. Once they come in contact, if one part neutralizes, then there are other forces at work that are going to make them rotate. It depends on how long they're in contact, because eventually they'll neutralize. But for the instant, we're just looking at whether they come together. That's a great question. That's a really, really good question. Okay, just a few more. Actually, you know what? No, the rest of them are repeats, so like, that's good. I don't think we need any more, because it doesn't cover any new ground. Yeah?
So if it was like a negative big quantity of Q, and they're both insulators, what exactly would happen?
That is something we can't answer without more information.
Okay.
And a really, really good question. Those are the best kind, because that requires a lot more thought. So is it big enough to force charges even though it's an insulator? Is there enough charge on there so that the charge will move anyway? We know we can charge things that are insulators, because I charged up the balloon. The balloon was an insulator, and we can charge it up. But I don't know if you remember, but I had somebody hold the balloon and I held the rod near it. And it was hard for me to find the right spot on the balloon, because the entire balloon didn't charge up, only that one spot. So if they're free to rotate, that would change whether or not it discharges the whole thing. We could get areas of differential charge on the same object. So one side could be positive and the other side could be negative. So really interesting scenario, but a little more complex than we want to get into right now.
Okay.
Fun to think about though, isn't it? I think so. Okay. At the end of last class, we talked about quantifying these forces that we've been talking about. So we know that there's an attractive force between opposite charges. We know there's a repulsive force between like charges, but we didn't talk about how much. We didn't talk about the magnitude of that force. We didn't talk about what makes that force bigger, what makes that force smaller. Well, we kind of did. We said that if you have more charge, you have more force. I want to know exactly how much though. Like physicists, we don't just say, oh, there is some force. We want to know exactly how much We want to know what direction it's in. We want to know what factors influence it. All of the above. And I gave you an equation for exactly that. Find exactly how much force there is between charged particles. We call it Coulomb's law, and it looks something like this. So the Coulomb force, or the electrostatic force, equals K Q1 Q2 over R squared, and it's in the R hat direction. I mentioned that that R hat unit vector is just a notational tool that tells us what direction it's going in. The force is going to be in the direction of the radius between the two. I use the word radius because it's an R. It's just the straight line distance from one charge to the other. K was a constant. And I gave you an equation for K, and I told you we're not going to use it right away, but it's something that we'll use later on. 1 over 4 pi epsilon 0. 1 is the number 1, 4 is the number 4, pi is the number pi, all constants. Epsilon 0 is also a constant. It's called the permittivity of free space. We'll talk about that later when we get into electric fields, and specifically when we get into capacitors. It's, if I'm remembering right, 8.85 times 10 to the negative 12th, but we're going to cover that when we get to it. It essentially just tells you how easy it is for electric fields to move through the universe. Electric fields move through stuff, and it can move through empty space, which is amazing because not very many things can do that. Like if I yell in outer space, you can't hear me because sound waves can't move through space. They need a medium to carry them. But electric and magnetic fields can move through empty space, which is how light gets from the sun to us, which is awesome because, again, that lets life happen on the planet. If it wasn't the way it is, then we wouldn't have existence like we do. So that's kind of cool. I like existence. Similarly, that permittivity of free space tells us this idea of force at a distance. It was a way of us finding the speed of light when we originally discovered that light moved at a finite speed. So there was an experiment in Cleveland, Ohio, of all places, Case Western University. Yeah, you've heard of this place.
Yeah.
Where two scientists, Michelson and Morley, did an experiment, and they thought that there must be something carrying light waves through space, because every wave needs something to carry it, like water waves have water to carry it, sound waves have air to carry it. Light waves must have that as well, right? It's logical, they're a wave, they must have something to carry it. So he said there must be this invisible, they called it the ether, that the universe is full of. They were trying to discover the ether, but they actually discovered instead that there is no ether. And as an accident, they discovered the speed of light, which is pretty awesome. We'll talk about that in a bit more depth again later in the semester too, but I sometimes just can't help myself. Talking about physics is so fun. Do you guys ever tell people about physics stuff? Like, you find yourself explaining physics to people?
Maybe after this class.
That's a real shame. You really should. I've ruined so many movies for my friends and family because I explain the physics of what's going on. I love it. All of these things are constants, which makes this a constant too. If everything that makes it is not changing, then it's not changing either. And I can just give you the value of it. 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Yeah.
When you're like on your you see some physics thing going on, are you like, oh, that's physics?
Yes.
Like anything?
Yes. Absolutely.
That's kind of cool.
I teach karate classes a couple days a week, and I always link them to physics. I have a disc golf YouTube channel where I do disc golf physics. So, but yeah, it permeates all aspects of life, if you want it to. And it's kind of cool when it does, because I feel like I understand stuff better when I get fundamental understanding of it. And all that is physics, no matter what it is, whatever your hobby might be. Physics advanced, right? Yeah, heck yeah. If you know the two charges and you know the distance between them, this is a constant, you can find the force. Why don't we try it? What is a hydrogen atom made of? This is not a hard question. I know you aren't in chemistry class, but what is a hydrogen atom made out of? It's the most abundant element in the universe. So what?
It's hydrogen.
You did try. You're the only one who did. So you win. They all lose. Hydrogen is very simple. It's number 1 on the periodic table. It's number 1 because it only has one proton. So it has one proton. And things that have one proton will also have one electron. What is a hydrogen atom made out of?
One electron.
One electron and one proton. That's exactly what it's made out of. If it was deuterium, it would have a neutron in there, I think. If it was tritium, it would have a couple neutrons in there. That's important if we get to nuclear stuff, which I don't think we're gonna. Fusion reactions use deuterium and tritium, but that's neither here nor there. We have a hydrogen atom. We know the charge of those two things, don't we? Don't we? You better, because, I mean, the first question might be a little obscure, but this one I've told you several times, even today. What's the charge of the proton?
1.602 times 10. Yeah, you got it. You got it.
What's the charge of the electron?
Negative.
The same thing.
All right, I looked up a distance. I don't know how accurate it is for the distance between these things, but I just looked it up and we're going to use it. Thank you, Google, for everything that you do. You find where I wrote it down. Found it. So I looked up a distance and it gave me 2 times 10 to the minus 10th meters. I can immediately tell you a couple things regarding the answer to this without having done any math. I look at that and I say if I multiply k, which is a constant, a positive number, times q1 times q2, one is positive, one is negative, divided by r squared, which anything squared is going to be positive in the end, I'm going to end up with a negative number. And a lot of people in Physics 102 get confused by that. They say it's negative, what does that mean? Well, negative does imply direction, but because it's in the r hat direction, it's in the negative r hat direction. If I drew a straight line from one to the other, it would be like an arrow drawn from one to the other. The negative means it's in the other direction of that arrow. So if I drew an arrow from the positive to the negative, a negative answer would be pointing that way. So what does a negative answer mean in a Coulomb's law equation? It just means that the forces are towards each other. It's towards the source of that force. Whatever's causing that force, I'm being drawn towards it. And you told me that before. You already knew that. It's an attractive force. The positive and the negative is almost irrelevant if you know the charges involved. You know the direction. It's either towards or away, attractive or repulsive. If you're a mathematically minded person and like the positives and negatives, leave them. Otherwise, you can just do an absolute value and figure out the direction later. That's important that you all hear and understand what I just said. Don't let the positives and negatives confuse you. If it's easier for you, do the absolute value and figure out the direction based on what the charges are. Fair enough? It becomes particularly tricky when we do two-dimensional. Right now we're doing one-dimensional. It's in a straight line. It's in the x-plane. When we have an x and a y, which I'm hoping to get to today, but probably not gonna, then it gets more complicated because you have to do a little bit of trigonometry. Yes?
Wait, you said if they're, it's a negative meters in between them, like the force distance, they're attracting each other?
Yeah.
Okay.
If it's negative, that just means one of them is a positive and one of them is negative, right? If they're both negative, we end up with a positive answer. If they're both positive, we end up with a positive answer. So it's the same thing. I'm just repeating the same thing in different words. But that can be confusing. So I wanted to make sure I was very upfront about it. It does get confusing and complicated when we start doing 2 dimensions. We're not going to do 3 dimensions. That's more than the scope of this class. But even 2 dimensions is a little bit complicated and requires trigonometry. This doesn't. It's a straight line. We only have to do 1 iteration. All right, so I know it's going to be an attractive force. The electron is going to feel a force this way. The proton is going to feel a force that way. I don't need the positive and the negative to tell me that. It does tell me that, but I don't need it because I already know that once they're opposite charges, they're going to feel an attractive force. I know that it's along the radial line between them. Cool. To find the magnitude of the force, to find how big the force is, now that I know the direction, I just need to use Coulomb's law. F equals K, Q1, Q2 over R squared. R is 2 times 10 to the negative 10th. I highly recommend you practice putting these in your calculator instead of just watching me do it, because it's a little tricky using the exponents and taking squared of things that are in scientific notation. And every calculator behaves a little differently, so I highly recommend you play along at home. You do it as well. Your calculator doesn't work like my calculator, so watching me do it isn't really good practice. All of that being said, let's do the calculation and see what we get. K is 8.99 times 10 to the 9th. Multiply that by 1.602 times 10 to the minus 19. Multiply that by 1.602 times 10 to the minus 19. And you say, Dr. Johnson, it's supposed to be a negative 1.602 times 10 to the minus 19. Well, that negative is all about direction, and we already know the direction. So I'm just going to do the absolute value. If you want to keep the negative in there, that's fine. Maybe your OCD is different than my OCD. That's okay. As long as you understand and can get the right answer, I'm happy. All right, all of that is going to be divided by the quantity 2 times 10 to the negative 10 squared. Don't forget to square the bottom. Don't forget to square that distance. If you do not put the squared in, you'll get the wrong answer. Allow me to reiterate that important point. Don't forget to square the bottom. If you don't square the bottom, the r, if it's not r squared, it won't be correct. I get my answer, and I get 5.77 times 10 to the minus 9 newtons. If that's what you got on your calculator, awesome. Tip of the hat to you. If it's not what you got, then you type something in wrong. Yes, sir?
You round it up to like 6.
You can. So when I grade quizzes and exams, I don't know how sensitive the homework system is. I don't know what decimal point they go to or how many sig figs. I've never used it before, like I said. But when I'm grading your test, I'm going to look at your process. And if it's the right process and you round it to, if you round this one to 6, that's a little bit of a big rounding, but I'd probably figure out what you did and say it was right, probably. If not, then you come talk to me and we talk through and make sure that you're thinking right. If you rounded it and got like 72, then that's not a rounding error, that's a mistake somewhere along the line. So the process is every bit as important as the final answer. Are you not getting the right answer?
I'm getting hands.
Oh, typing in something wrong.
I'll try.
That's why we're doing it, because you wouldn't know that was a problem, and you don't want to discover a problem like that on your exam, right? Sitting at a quiz and like, oh my God, that's wrong. Are we comfortable with this? How do you think this compares? First of all, is this a big number or a small number? It's pretty small, but we're talking about electrons and protons, and those are pretty small things. It doesn't take a lot of force to move something with really, really small mass. So it's small for like moving a desk or launching a rocket. But for moving an electron, it's actually a pretty sizable amount of force. It is a very small number though, 10 to the minus 9th. I wonder how that would compare to the gravitational force between them. Yes, sir?
What is the unit for it?
It's a force, so what's the unit going to be? Newtons. Let's check though. You know what? I'm glad you asked because we need to make sure they're right. And unit analysis, how many of you have to take the MCAT or some similar type of test? If you don't remember an equation, you can just look at the units and figure out the equation about half of the time. Let's double check. Let's make sure that it's right. Q and Q are both in coulombs, right? So it's coulombs times coulombs. That's coulombs squared. R is in meters, and that's squared. So it's coulombs squared divided by meters squared. And then what's the unit for K? Newtons on top, meters squared on top, coulombs squared on the bottom. I multiplied it by coulombs squared on the top and meters squared on the bottom, so the meters cancel out and the coulombs cancel out. Leaves us with newtons. We got our right unit. So, did you just ask me what the unit is? The thing I just said? Oh, that's okay. You can ask the question. I'm sorry that I missed. You didn't do anything wrong. That's my fault. So one more time, just because people were still working. I should have waited. The units, they do work out. We just checked it with the equation. It's a force. It comes out to be newtons. Anytime we find a force, it should come out to be newtons, in this class anyway. I mean, it could be pounds, right? That's a force too. But we don't normally use that system. We normally use newtons. Standard system international. Yeah.
What about the R hat that you did earlier?
The R hat is just about direction. It's in the R hat direction. We can imply direction in lots and lots of different ways.
Mm-hmm.
In general, it's along the line of the radius between the two.
So you don't have to like plug anything in, that's just kind of like there.
As long as you include the direction, and as I said at the beginning, we were just finding how big the force was, just the magnitude. The direction we add in however we want to do it. We can say it's towards the positive, towards the negative. If I said what is the force on the electron, it's not up there, but what is the force on the electron? You could say 5.75 newtons towards the proton. And that's what R hat means. Yes, sir?
Could we also just say that with a negative?
What's that?
Could we also just say that with a negative or like a positive?
You could, as long as you indicate what your coordinate system is. So negative is to the left, right? Remember from physics 1, you get to pick what was positive and what was negative, but you have to be clear what it means. So like if I drop something, sometimes my calculations are easier if I just call down positive, but if I don't indicate that, it doesn't, the reader wouldn't know. So you just have to let me know. So yes, the answer to your question is absolutely yes.
But isn't negative like they're always going towards each other?
No. Well, yeah, in this case, a negative implies they're towards each other, but I don't know if towards each other means down, or towards each other means up, or towards each other means left, or towards each other means right. If you have a picture and it's drawn, then it's indicated. Yeah.
I know that you said the homework program that we're using is new and you're not sure like how it.
It's new to me.
Yeah.
People in the room might have to answer.
There are problems like this on there, and I thought that maybe I was doing them wrong because I was getting the answers wrong, but it's like I'm doing them right. But every time I go type in something in scientific notation, it says it's wrong, and then I clicked on this one link, and then it gave me a list of like all of the things that it will not.
Anybody else try them and not
Yeah,
have
you have to use
You
E.
have to type in.
Oh,
just a capital E.
And then you use like 4 or 5 decimal places because
It's very picky.
really.
That's frustrating.
Yeah.
To a degree, yeah.
Or you can just type in the number too, the long version of it.
Right, yeah.
So this is all good information. I appreciate the info. Have you tried it with the ones I set up? Because there's also a non-zero chance that I messed up how I set it up. So these are things we want to discover as quickly as we can to get fixed. All right, we have time for probably one more. I was going to do the gravitational calculation, but maybe I'll just tell you. The gravitational constant is 6.67 times 10 to the negative 11. That constant is tiny, right? If we were to calculate the gravitational force between the proton and the electron, it would be virtually insignificant. It would be so small, it would be probably 10 to the minus very large number. I don't remember the exact number, but I have it written down. The gravitational force between a proton and an electron at that same distance, given their masses and given that gravitational constant that I just read to you, would be 2.5 times 10 to the negative 48th newtons. Negative 48.
Could you say the constant again?
What's that?
Could you say the constant again, the value?
The gravitational constant? I'm not gonna test you on that, that's from last semester. It's just kind of fun to know stuff. We think of gravity as a very powerful force because it's one that's in like every aspect of our lives. If I try to lift a desk, desks are heavy, or a refrigerator or something, and that's because of gravity. But as it turns out, gravity is fairly weak, which is the point of what I'm trying to say. The gravitational force between the two things that we just calculated is orders and orders of magnitude less than the electrical force between them. You said the electrical force between them, which was, I think, 10 to the minus 9th in order of magnitude, is small. But how much bigger is that? It's like 5 times in orders of magnitude bigger than the gravitational force, which is wild. The gravitational force is very, very small compared to electrostatic forces on similar scales. Isn't that wild? I thought so. You want to do another easy one, or you want to start a hard one and finish it next class? You start a hard one?
Yeah.
Okay. Or we could talk about the superposition principle and just start the hard one next class, so we can do it without a break in the middle?
Yeah, let's do that.
Okay. I think that's the best plan. So, at its most basic, what we just did is Coulomb's law. And it only gets complicated when you start moving stuff around in different orientations, but it's really just doing what we just did with vectors. So you have to find out directions in the end. So that's the meat of electrostatic calculations. Everything else we do from here on out has its foundation in what we just did. So if you're good at that, it does get more complicated, it does get confusing. I'm not going to lie to you. No sugarcoating here. It does get more complicated, and it does get confusing. But it is just different versions of what we just did. We'll do some like that, like I said, next class. But what if we have more than one charge? We have our charge here that we're looking at, and we have a charge over here, then we have a charge over here, we have a charge over there. What if we have a whole bunch of charges, and we want to find the force on our original charge? Coulomb's law only has 2 Q's in it. How do I deal with all of those things? Well, as it turns out, those forces from all of those different charges all do happen, and they're all happening at the same time, but they happen totally independently of each other. So I can just do Coulomb's law for this one, and I can do Coulomb's law for this one, and I can do Coulomb's law for this one, and I can do Coulomb's law for that one. And I get a bunch of different force vectors acting on my one charge, and I just add them up. But I have to add them like vectors. Now, you guys remember, like, when we did force vectors originally in Physics 1, I don't know if Dr. Jones did it, but in our class, I talked about if I'm pushing the desk this way and if somebody else is pushing the desk that way, we get a combination of those 2 forces, and we have to do a little bit of trigonometry to add them up. It's the same thing. You just have to do it for every single charge that's pushing on the initial charge that you're looking at. That's the superposition principle. The charges superimpose, the forces superimpose on that charge. So if I've got proton A and proton B, they're going to repel each other. But if I have proton C over here, it's also going to repel it. And I have to figure out the individual forces using Coulomb's law, and I have to add up the force vectors using trigonometry. Whew. As much fun as that sounds, it gets a little easier because eventually we're going to talk about electric fields. Electric fields are more abstract, but very, very useful. I think we're out of time. Is that clock right? All right, folks, good job today. We're going to pick up with a little bit more difficult problems next class and superposition principle example.